I'd like to start immediately and catch up with time a little bit. This is only one of the aspects of what Mr. Kaufeld already addressed. What is the effect of refrigerants with a high temperature glide on condensers and evaporators? I would like to start with a brief basic section, and I'd like to be as short as possible to make sure that we have the same understanding of temperature glides and pressures, what we are talking about, what the terms are that we are using. Then I will talk about the effects of the new EU directive on condensers and evaporators and some basic principles and basic knowledge about the temperature glide and refrigerants. Then the main part will be the second item of the agenda. What is the influence of the temperature glide on our devices, our systems, our heat exchangers? What are the effects? And what are the consequences for the system or for the refrigerant or the refrigerated good? Mr. Kaufeld, Professor Kaufeld, already mentioned the mean temperature method, and I am going to explain to you how it works, how it is being applied, and why does it make the design of systems better using this method. These are the basics. Many of you have seen this chart, I'm sure, several times over the last few months. I'm not going to explain it in detail. You know the face-down scenario. This is what you see here from the new F-gas regulation. I'd only reiterate 2 points here. The first one is that we have this GWP value of 2,500 that will be effective as of 2020 for new systems and plants. And the second point that I'd like to address is the first drastic drop here by 37% in 2018. So 2018, that's basically tomorrow. And it's important that we are all in the same boat as of now in order to reach those goals. In order to reach the limit values, the industry has only two opportunities. Well, first of all, they can use refrigerants with a low GWP. That's clear. And that includes the natural refrigerants, CO2, NH3, propane, water, everything that we've already heard during the previous presentation. Also new synthetic refrigerant blends with the lower GWPs, and they're called low GWP alternatives. As this slide shows you, the planned GWP is the division here between the charge multiplied by the GWP divided by 1,000 in tons. This leads to the second variant, how you can calculate the limit values, the refrigerant charge. We've already heard a little bit about this, and we'll hear more about this during the course of the day. And this brings me to the next point. Condensers and air coolers with smaller tube volumes of tube diameters will become more and more a standard in the future. That means they need to be more efficient in order to reach the capacity of previous systems. And the second point is that all heat exchangers, condensers and air coolers will be operated in the future with the new synthetic refrigerant blends. If they have 4 in advance, so if they're from a 4 series, they are zeotropic. That means they have a high temperature glide. And this is a challenge we have to face as an industry, and we in Güntner in particular, because we are the manufacturers of heat exchangers. In my presentation, I will only talk about the temperature glide, the refrigerant temperature glide, but more about that later. This is an overview of the 4 series refrigerants. These are the 400 refrigerants that you can find with our selection software that are suitable for our design of our systems. Here you can see the middle glide. So there are refrigerants with high glides of almost 8 Kelvin, but you also have refrigerants, the 410A, with a very small glide. In addition to that, I've listed the GWP, the global warming potential, and I've marked all those refrigerants in red with a GWP higher than the limit that will be effective as of 2020. So 2,500, that's the limit. So if you look at the figures, so you will see that those that are taken out have a smaller temperature glide, and those with a small GWP have a high temperature glide. It's not so clear in this table, that's why I've created a chart from it. The medium temperature glide is listed in Kelvin here, so you see the GWP of each refrigerant, and the bubble size of the chart shows you also the GWP. What this chart shows to you is that above this limit of 2,500, that these are refrigerants that won't be used after 2020 anymore. They're not allowed anymore. The R404A, for example, they had a small temperature glide. All of the other refrigerants, and you can see that line here, the lower the GWP, the higher the temperature glide. And this is what we will be affected by, all of us will be affected by in the future. Why do we have zeotropic blends, refrigerant blends in the future and not azeotropic ones? I'd like to explain this by looking at R449A. This is a refrigerant blend of 4 components with almost equal mass proportions. But the difference of these 4 refrigerants is their normal boiling point. And that's quite different when you look at the different refrigerants. The R32, for example, has a normal boiling point of minus 52 degrees Celsius, and the R134A minus 26. So 26 Kelvin is the difference here. So if you evaporate this blend, what evaporates first is the component that has the lowest boiling point. And then with the increasing boiling point, the components will evaporate one after the other. Of course, they evaporate at the same time, but still subsequently. And this will make the temperature rise. For the condenser, it's the opposite, because the chart is contrary. The one with the highest boiling point will be condensed first of all, and the component with the lowest boiling point will be condensed at last, which means that the condensing temperature is going down, is decreasing. This is what the chart looks like. The temperature curves are not in parallel to the isobars anymore, but they are helical. The temperature is always higher than the boiling point temperature, and the difference or the discrepancy here is the temperature glide. An interesting side aspect is I've mentioned the average or the medium temperature glide already, and if you look at it in detail, you'll see that the temperature glide at different temperature or pressure levels, you'll see that with a condenser of a dew point temperature of 45 degrees Celsius, the temperature glide is lower than with a dew point temperature of minus 30 degrees. So the temperature curves here will be rather flat, and down here they become steeper. What this also means is that the temperature glide in a low temperature has a higher effect on a low temperature condenser than a normal temperature condenser. So the temperature glide is never identical, it's never the same, and therefore the effect is different. But what is the actual influence or the effect of the temperature glide? What is the effect on condensers and evaporators? I'd like to start with the condensers. When you select a condenser, you usually consider different criteria. The noise level pressure or the brand name of the manufacturer, for example. From a thermodynamic point, you also look at the temperature difference and the capacity. The temperature difference between the condensing temperature and air inlet temperature at the condenser inlet. This delta T, with this delta T, you create the framework conditions that have an effect on the middle temperature difference or mean temperature difference that's effective on the condenser. It's the delta theta M. The capacity, the air inlet temperature and the condensing temperature is what's entered in the system, and this is how you create the boundary conditions or the framework conditions. Then the software will give you a device with the right K value, K multiplied by A value. So the delta T that you enter has a direct influence on the parameter size of the condenser. So large delta T means a smaller condenser, smaller delta T means larger condenser. So this interaction is quite simple. Or the logic is the ratio. If you ask yourself, what delta T should I select for my design, you can have a look at the VDMA 24/7 because they have created a standard sheet. It's existed for some years. Part 8, that is, Mr. Güntner Company also contributed to this standardized sheet. And it talks about the components of heat exchanger and the energy efficiency of refrigerating plants and the design of those. And that they said that the delta T should be between 8 Kelvin and 13 Kelvin. So let's have a look at the design of a condenser for 404A and a delta T of 10 Kelvin. That means you have a condensing starting at 45 degrees Celsius and an air inlet temperature of 35 degrees. And this is the device that will be selected with a surface area of 25 square meters. If you calculate the values or parameters for the same device with a different refrigerant, then you'll find that you have a lower capacity of 17% with the R494A. The question is, why is that? Is the refrigerant worse? Are there other reasons? And I'd like to give you the answer to this by explaining why that is. Let's have a look at the diagram, the chart again. Here we have the condenser, and the example was to find a condenser for the R404A with 10 kilowatt capacity, 45 degrees Celsius, and a pressure of 20 bar almost. That means, according to the standard, we have the dew point temperature here. That's the condensing temperature that's set. That's the set point value. And for the R404A, we need a pressure of 19.44 bar. At the outlet of the condenser, the boiling point, we have 44.7 degrees. So 0. Kelvin is a difference. For many years, 0. Kelvin, since we've had R404A, that wasn't considered, it was neglected because the effect was neglectable, they thought. But for the R449A, we have a temperature of 40.5, and the temperature glide with 4.5 Kelvin is much higher, 4.5 times higher. And there you can see a direct effect on the condenser, and that could be the reason why we have this lower capacity by 17%. We have this temperature chart, the temperature place chart or space chart. This shows you the refrigerant of air and the refrigerant. So the refrigerant enters at 75 degrees as the heated gas, then it's desuperheated, and at this point the condensation starts, the dew point temperature. And then at the end here it ends. Air enters at 45 degrees Celsius, so you have this delta T of 10 Kelvin. If you look at this surface area, or if you integrated that surface area, that would get you the mean temperature difference that's effective on the condenser, and that's the delta theta M. And the reference point for the dew point temperature, I already showed that to you before, is the reference point is the dew point temperature. So this is the chart for an ideal condenser with a single component refrigerant. No pressure loss with this ideal condenser, a single component refrigerant. So here in this two-phase area, the temperature will stay at 45 degrees. This means that this red dotted line shows the ideal design, the ideal that you could reach. In real life, there is pressure loss with condensers, of course, and for that reason, for a single component refrigerant, the temperature curve for a refrigerant with pressure loss is the following. Pressure loss means that at the end the pressure is lower than at the inlet point, and therefore the refrigerant temperature decreases. But the effect is so little that I really would have to mark it here. It's only very few degree Kelvin. But we only have this green area as the temperature difference, so this pressure loss is lost in the capacity, or means a capacity loss. When you look at the real condenser, if you operate it with a zeotropic refrigerant, then the temperature curve looks as follows. We've already heard that the condensing temperature decreases. So here towards the end, this triangle will be a driving factor for the temperature difference. And this is where we lost the 17% in the capacity, because here the delta T is much smaller, of course. So as a short interim conclusion, I'd like to say that the temperature glide of the refrigerant leads to a reduction of the temperature difference on the condenser. And therefore, the capacity is lowered because of this delta T. If you want to install those 10 Kelvin nevertheless, you would have to select a condenser where the dew point temperature rises. So the condenser with this design would have a higher capacity. And the positive side effect is that the capacity of the system is higher because the temperature of condensation is lower. What about the evaporator? The evaporator is selected according to a similar principle from regards of a thermodynamic criteria, but here the temperature difference dT1 is the air inlet temperature in the evaporator minus the evaporation temperature. That's the delta T. And the same situation as for the condenser applies. You enter all the values, and then the software calculates does the right calculation and selects the right system for you. The temperature difference on the evaporator has the same effect than it has with the condenser: smaller delta T, larger delta T, smaller evaporator, small delta T, larger evaporator. The recommendation of the VDMA is 7 Kelvin to 10 Kelvin. But the difference to the condenser is the following. The delta T that you have here has a direct influence on the dehumidification of the cooled good. With a large delta T, there's more dehumidification, and with a small delta T, there's less dehumidification. Let's have a look on the design of an evaporator with 404A, 0 degree evaporation temperature, and a surface area of 80 square meters, Then the same system with R449 has a capacity of 27.5 kilowatts, so 26% more capacity. So if you want to sell the entire system, you've done everything right, because the condenser is higher, but the evaporators are much smaller. So in total, overall, you've come to a good result. But that's not true, and I'd recommend not to do that, because the dehumidification capacity is twice as high if you do not look at the temperature glide. So if a system with unpackaged cooling goods, you have a massive problem in the end. What's the reason for this? We'd like to look at this chart again first. For the evaporator, the example was again the 404A. We were looking for an evaporator with a capacity of 20 kilowatt, 0 degrees evaporation temperature, and the evaporation temperature reaches the dew point temperature here at this green point, and the pressure is at 5 bar. The boiling point temperature would be minus 0.5 degrees, so the temperature glide can still be neglected. It's so small. With the 449A, you have a temperature glide of 4.6 Kelvin already, and the effect of this is what I will show to you in this temperature place chart for an evaporator. In red, you see the refrigerant. In blue, you see the air again. The single component refrigerant enters at 0 degrees, then it's evaporated. Once it's completely evaporated, superheating starts, and air is cooled down as a consequence. So this is again for an ideal evaporator with a single component refrigerant with the temperature glide. And the integrated surface describes the mean temperature difference, delta theta m again, and the reference point is again at this line, on this line, and what's in red is what you want to reach, what's the ideal. For the evaporator with pressure loss, a similar situation occurs than you had with the condenser. The pressure loss takes away delta theta m, so the capacity is lowered. That applies both to the condenser and the evaporator.
And for a zeotropic refrigerant blend, we see that the dew point temperature is set as evaporation temperature. If you use a refrigerant with temperature glide, the refrigerant which is heating up in evaporation has to enter the condenser at a lower temperature to have 0 degree temperature at the outlet of the condenser. In addition to the previous area, we gain the purple area, so capacity goes up because we have now available the whole purple area. But if you evaporate at -2 and you want it 0, then the surface on the condenser will be bigger, and the humidification will go up. So the temperature glide of the refrigerant leads to a larger driving temperature. If you neglect the evaporator's capacity, you can select smaller condensers. But since the surface temperature is lower, dehumidification will increase many times over. That will be the effect. The question is now, if you don't want that to happen, if you select a slightly smaller, if you wish to select a slightly smaller condenser and you have a stable dehumidification performance, what can you do? You can use the middle temperature, the mean temperature method, or as it says on the slide, the middle temperature method. So let's remember this diagram for the condenser. We said that the dew point temperature is the reference point for the condensation temperature, and the temperature line of the zeotropic refrigerant blend goes down, as you see here. What do? The reference point for the condensation temperature is shifted in the mean area, the central area of the two-phase area. So in these areas, our delta T is slightly higher, and down here, delta T is slightly smaller, slightly lower. In the arithmetic average, delta T will stay stable, as if we use the one-component refrigerant. So we reduce the influence of the temperature glide. As a consequence, well, here we had 45 degrees, which we shift to the mean area, to the central area. The dew point temperature will slightly higher. In the area of the desuperheating area, our delta T will be slightly bigger as well. So with this design, our capacity will be slightly higher than with one component refrigerant. In the halopedia diagram, we have the dew point temperature as condensation temperature, which we shift into the central area of the two-phase area. So we condense at slightly higher pressures. So the temperature, the mean temperature is here 45 degrees. This would lead to a slightly different dew point temperature with 449A, 22 degrees, more or less. You enter these data in the software and you'll be fine. If you do that and you design, this is, by the way, the same plant, 449, 47.2 degrees Celsius at the inlet. The capacity will be 10.8 compared to 10.2 previously. So this is a result of the higher delta T in the entry area. Evaporators. Here we act similarly. Again, we shift the evaporation temperature in the central area of the two-phase zone. The effect is identical. The light blue delta T is the same as with the one-component refrigerant, because here we gain delta T and here we lose delta T. At this point, it's understandable why the dehumidification capacity is okay. Here we evaporate at 1, in the beginning at 1, +1 in the central area 0, and at the end -1 degree. So it's the same. So it's an offset process. So you have 0 degree. Our dew point temperature goes up, so we lose delta T in the superheating area. Evaporation in a design like this will have a lower capacity than a one-component refrigerant. In the halopedia diagram, we shift the mean temperature and evaporate at higher temperatures. So here we have a new dew point temperature. This leads to an issue. It's not as easy as with the condenser, where it was easy. We had the dew point and the boiling point temperature divided by 2, and we knew exactly where we are in the middle area of the two-phase zone. Here with the evaporator, it depends on where we condense. If we condense at a lower temperature, the evaporation temperature will be here or there, or you have subcooling. So the temperature depends on the state of the refrigerant at the outlet of the condenser. So this is highly innovative. To solve this issue, the corrected evaporation temperature would be 1.9 Kelvin. This gives you the 20 kW, which is slightly lower than with 404A. So the condensate capacity will be as high as always. So this will enable you to store unpackaged fresh goods at normal temperatures, as with one component refrigerants. So the question arises, how is it done? How can you work with this mean temperature method in your everyday life? If you are really clever and smart, you just make a sketch and include in this graph all the most frequently used refrigerants, or else you opt for calculation tables, as I have one example here for R449A, where you have the mean condensation temperature, and in the next column, the corrected dew point temperature. This is quite basic for the condenser. You just look up in this table, well, 45 degrees, the mean condensation temperature, and here you read out, well, my dew point temperature is 47.22. With this corrected dew point temperature, you look up your software, you enter this data, and you get the right result. With the evaporator, as I said, we depend on the outlet state of the refrigerant after the condenser, so it's more complex. So this is again a table for R449, and the condensation temperature is 45 degrees, and subcooling has a role to play. Subcooling is here entered in Kelvin. And in this column, you look up the desirable mean temperature you wanted. In our case, 0 degree, and you go to 0, and you find 1.94, which is our corrected dew point temperature, which you enter in the software, and the software will deliver the right result. This you can do if you like and have available such tables, provided that you have a software which calculates, including the thermophysical properties of these refrigerants. If dew point is calculated and the software doesn't know about it, it is to no avail. But cheer up, I found a software which helps out in these cases, which is a software which includes thermophysical data of more than 40 refrigerants, among them 449, 468, and all other new refrigerants you might think of. It calculates correctly, including all chemical data, thermodynamical correct calculation. It is available in 16 languages, can be used all over the world, achieves highest customer satisfaction. And this is a quotation, by the way, and it's not my quotation. This program is labeled as the gold standard in design of such devices. And this product is called Güntner GPC 2015. So I urgently recommend to have a look at this program if you're not running it yet. If you have installed this program, I have some good news for you, and I'd like to take the opportunity and thank our software team for providing such a high quality. The GPC will have an update next week, and after the update you can enter not only dew point but also mean temperature. So starting next week, if you want to design a condenser or evaporator of the Güntner product range, you can either enter dew point or the mean temperature, and the software just recalculate. You enter your data, and the software will do all the rest. So as a result, you'll get such a data sheet with the calculations. Some things have changed. In former times, you had dew point temperature, beginning of condensation, and if you go to mean temperature, it will say mean temperature, and condensation temperature will be corrected automatically, which is a very nice feature. So much for the mean temperature method. And I think this brings me to the end of my presentation. I hope I could catch up on time and at the same time provide you with the information that all the efforts we make in our work make sure that you can use every which means and fluid you wish with Güntner products. Do you have any questions? This is the time. Now or later today? I'm here and I'm available. I have a question. Zeotropic blends are sold as drop-in solutions for 404A plants. If you were an operator of a 404A plant, would you restructure your system? You can do that. This is something I did not touch upon in my presentation. This was the design for new plants. The drop-in case should be looked at separately. You're quite right here. I talked to partners in the future, and I'm going to look at it in the future. And here, of course, the situation is different. The situation is highly complex. Without any paper or presentations at hand, I find it difficult to fill you in on that. If you have an uncontrolled compressor, then you'll have a problem. Is that an answer to your question? Thank you. Hello? I have one question. The GWP values, where do they come from? I have the value, I know the value for 410A, and it differs from what I saw on the table. So have there been any changes any lately, or what? The mean GWPs? Were you talking about glide or GWP? GWPs. The GWPs I have on my presentations are taken from the last amendment of the directive. Thank you. Any further questions?
Okay.
Thank you very much, Mr. Freiherr. Thanks.